Hunting from the air is one of the most complex feats that evolution has produced. Navigating a three-dimensional world while trying to catch prey that has equally impressive escape tactics is no simple matter. When we think of aerial predators, we often think of fierce birds of prey like the peregrine falcon. Sometimes they swoop past their prey and then rocket up from below to snatch the victim in midair. But some studies have shown that the overall hunting success rate of the peregrine falcon is 23.1%. Other aerial predators, like hawks, select individual prey from a flock with a similar success rate of 22.5%. Species like owls hunt by pinning their prey to the ground. Although they lack highly developed aerial hunting techniques, they still have a success rate of about 25%. Other top predators on Earth rarely exceed this number. Lions are successful in less than 30% of their hunts. African wild dogs are perhaps the best terrestrial predators, with a success rate of over 70% when working together. But this number still pales in comparison to a predator that isn't very impressive on the ground. To find this predator, you must turn your attention to a much smaller creature. They hover near bodies of water with beautiful wings and large compound eyes. This is the dragonfly. The hunting success rate of the dragonfly is an impressive number. They achieve nearly 100%. Dragonflies belong to one of the oldest insect orders, Odonata, which has existed for nearly 320 million years. Their presence in the fossil record is relatively complete and shows that their morphology has remained largely unchanged over time. However, the size of dragonflies has changed significantly. Their ancient relatives were giants compared to the species that exist today. So what is it about the dragonfly's morphology that makes it the most effective predator today? And if this morphology is so effective, why did it gradually become smaller over the millennia? Why did evolution take away the world of aerial monsters nearly a meter long that once ruled the skies? Odonata means the toothed ones in Greek, and the name of these fearsome predators comes from their prominent, chewing mouthparts with sharp teeth located under the head. Dragonflies are also characterized by a freely moving head, very short antennae, large and highly developed compound eyes, along with rudimentary simple eyes, and two pairs of long wings. The only difference between extinct dragonflies and present-day dragonflies is their size. Some species from the Permian period had wingspans exceeding 70 centimeters, while the largest species today only reach a wingspan of 16 centimeters. Both males and females can be easily observed, perching and flying around aquatic habitats. Part of the reason for this is that dragonfly eggs must be laid in water. They often eat mosquitoes and other small flying insects that live in their hunting area. An interesting fact is that dragonflies can eat while flying. Although considered a relatively primitive insect, the dragonfly possesses some of the most unique and amazing flight adaptations compared to any animal, allowing them to achieve both high speed and great agility. One of the adaptations that dragonflies have, but which very few other insects possess, is direct flight muscles. Most other winged insects have what are called indirect flight muscles, which are attached to the thoracic wall and deform the thorax as they contract and expand. The deformation of the thorax transmits its resonance to the wings, causing them to vibrate and begin the flapping motion. While indirect flight muscles have their own advantages, dragonflies instead have individual muscles attached directly to the base of each of their wings. Being able to control each wing independently allows them to move and control each wing in 3 axes. This means they can control horizontal, vertical, and rotational movements. This gives the dragonfly a precision and flexibility that most insects with indirect flight muscles cannot match. With this independent control, the dragonfly is one of the few insect species that can propel itself in 6 directions: up, down, left, right, forward, and even backward. Another remarkable feature of dragonfly flight, compared to other insects, is the ability for their forewings and hindwings to flap out of phase with each other. And they can change this phase depending on the flight maneuvers they want to perform. One flight technique is called counterstroking, where they flap their forewings and hindwings 180 degrees, out of phase with each other. This allows them to hover or fly very slowly forward while generating significant lift. To fly quickly forward, dragonflies can use a flight style called phase stroking, in which the hindwing beats down before the forewing with a 90-degree phase difference. While this generates less lift, it produces more thrust, with some species capable of reaching flight speeds of over 50 kilometers per hour. This also, incidentally, makes them one of the fastest flying insects. Dragonflies can also use a flight style called synchronized stroking, in which both the forewings and hindwings beat at the same time. This flight style helps them accelerate quickly or change direction easily, because it generates a large amount of lift. However, they cannot maintain this flight style for long periods, so it is usually only used when chasing prey. In addition, dragonflies are capable of flying backward, a rare flight maneuver in other animals, except for some small flies and hummingbirds. They do this by tilting their body up at a 90-degree angle to change the direction of the force generated by the wings. Dragonflies can also choose not to flap their wings and glide freely, taking advantage of the lift from the air to move. In some special cases, the female can be carried by the male, as he uses his wings to propel both of them. The ability to switch between multiple flight styles and perform masterful aerial maneuvers is certainly what makes dragonflies such effective predators when hunting, flying insects, as well as when evading their own enemies. The dragonfly wing has a prominent feature called the pterostigma, which is a small colored spot located on the leading edge and is heavier than the rest of the wing. The pterostigma acts as a counterweight, shifting the wing's center of mass forward of the torsional axis at the pterostigma's location. This helps prevent unwanted oscillations, also known as flutter, at the leading edge of the wing when the dragonfly flies fast. Without the pterostigma, the dragonfly's wings would be prone to shaking, affecting its ability to glide at high speeds. This phenomenon is not only dangerous for dragonflies, but also affects larger man-made structures like airplanes and buildings, and it was the cause of the collapse of the Tacoma Narrows Bridge in 1940. For the dragonfly, a tiny spot that accounts for less than 0.1% of its total body weight allows it to achieve flight speeds 10 to 25% faster than without this feature. Dragonfly wings are not completely flat surfaces. The wing veins create three-dimensional corrugations that improve flight performance. These corrugations help to stabilize the wing and prevent deformation due to resonance, allowing the dragonfly to easily adjust its angle of attack and generate stronger lift. But the danger of the dragonfly comes not only from its speed, stability, and control, but also from the way the dragonfly perceives the world around it. This is also a crucial factor that enables them to be excellent aerial predators. Dragonflies not only dominate in flight, but also have incredible vision. Their characteristic compound eyes are the largest in the insect world, consisting of over 30,000 individual lenses called a mythidia. Each lens acts as a small telescope, detecting light from the direction it is pointing. Because their eyes wrap around almost the entire head, dragonflies have nearly 360-degree vision, perfect for observing their surroundings and finding potential targets without having to move their bodies. This is very useful when they hunt during the day and detect objects through visual cues. With 30,000 ommatidia covering a 360-degree field of view, dragonflies do not have the same visual acuity as humans or birds. In return, they are extremely sensitive to motion, and this sensitivity is many times stronger than that of humans. A prey item usually occupies no more than 1 degree of a dragonfly's field of vision before it decides to pursue. This means that movement across just 2 or 3 ommatidia is enough for the dragonfly's brain to detect and process the motion very quickly, helping it to immediately chase the prey or avoid a threat. The dragonfly's eye also has regional specialization. The upper or dorsal region of the eye is most sensitive to short wavelengths of light, namely ultraviolet and blue. Many dragonfly species fly low over the water when foraging. This helps potential targets stand out more clearly against the blue sky. On the other hand, the middle and lower regions of the eye are sensitive to a broader range of wavelengths. This likely aids in the recognition and pursuit of other dragonflies, whether potential mates or rivals. The dragonfly usually approaches from the front or from above. It can also help identify stationary prey, such as insects caught in a spider's web. This is a prize that the dragonfly will occasionally steal from the spider if there are no flying targets. These visual abilities, combined with masterful flying skills, have created a formidable predator. However, it is the way these two factors are integrated that makes the dragonfly the most effective predator alive in the world today. But it's not just the wings or eyes that make the dragonfly a successful predator, but also its brain. The dragonfly's brain is highly optimized for hunting strategies, allowing it to predict where its prey will go, and the predator quickly moves to intercept the victim. The dragonfly's brain not only controls its superior flight and vision, but also provides it with an optimal hunting strategy. The dragonfly uses a strategy of predicting the prey's position and then moving to intercept it, rather than simply chasing after it. In studies of other predators, such as birds of prey and predatory insects, it has been found that there are two main strategies used when hunting. These can be tracking and interception, with the interception method being much more difficult to execute. The tracking method is simpler, in which the predator keeps the prey stable in its field of view and accelerates its approach. The predator approaches and gradually closes the distance to the prey, until its superior speed allows it to catch up. Meanwhile, the interception method requires the predator to fly a predicted path to a location where it thinks the prey will be. This is more complex because it requires analyzing both the position and speed of the prey and the predator so they can meet at the same time. However, if the prediction is accurate, this method reduces reliance on an absolute speed advantage, helping the predator conserve more energy by not having to fly fast and accelerate suddenly. Although the dragonfly has enough speed and agility to use a tracking strategy, it primarily relies on an interception strategy to hunt. In humans, learning how to intercept is a behavior that needs to be trained. But for dragonflies, scientists believe this behavior may be hardwired into their nervous system, directly linking their visual and motor systems. However, when using an interception method, the prey is rarely stationary in the dragonfly's field of view. This makes hunting more difficult. Studies show that dragonflies often adjust their heads almost in sync with their prey, keeping the prey in the regions of the eye with higher visual sensitivity for tracking. In fact, this synchronization is so precise that the movement of the dragonfly's head is not just a reaction, but appears to be an action based on prediction. The perfect combination of mind and body has made the dragonfly the species with the highest hunting success rate that researchers have ever recorded. In 2012, researchers at Harvard found that dragonflies caught about 95% of the prey they pursued. This is an incredibly impressive number for any animal, especially for a flying one. The dragonfly will consume any flying prey that is the size of or smaller than its head, such as bees, moths, flies, or mosquitoes. Larger species can even catch and eat other dragonfly species. But if they are the best predators, why did evolution push them to hunt small prey? And why couldn't dragonflies continue to be giants with 70 centimeters wingspans and hunt larger prey? There are two main hypotheses about the reduction in the size of dragonflies, and neither is mutually exclusive. The first hypothesis suggests that 300 million years ago, the oxygen level in the atmosphere was much higher than it is today. It is thought that this abundant oxygen could support larger insect bodies because they rely on the process of oxygen diffusion through small holes in their exoskeleton for respiration. As oxygen levels drop to their current levels, the maximum size that an insect could attain also decreased. The second hypothesis suggests that about 150 million years ago, when small flying dinosaurs and birds began to evolve, they may have competed with large dragonfly species in the same environment. Since birds primarily hunted larger prey while dragonflies targeted smaller prey, smaller dragonflies faced less competition and were more likely to survive. Very few insects have achieved the success of the dragonfly, a species that has existed for a relatively long time and remained unchanged for hundreds of millions of years, with perfect adaptations that have helped it maintain its position as a top predator. It is no surprise that engineers and scientists are eager to study and copy the flight and hunting capabilities of the dragonfly. This impressive insect has become a source of inspiration for many biomimicry projects aimed at recreating how they track targets and perform acrobatic flight maneuvers. To date, no small-sized drone comparable to a dragonfly can fly freely in the air, but there have been some prototypes of micro-air vehicles under development. So, the next time you see a dragonfly flying around a pond near your home, take a moment to admire this sky assassin, and be grateful that they are as small as they are today. Or at least, be glad you're not a fruit fly. While morphology is important to the long-term success of the dragonfly, their behavior and life cycle are just as crucial. Dragonflies not only dominate the insect skies, but their larvae are fearsome underwater predators with jaws that can extend half their body length. The world of the dragonfly larva is even more bizarre than that of the adult dragonflies we are familiar with, and their hunting strategies are far more terrifying. And are you impressed with this unique insect? Leave your thoughts in the comments below.